All right, guys, we're going to get started with going over this problem. So this problem says a rock is thrown horizontally from the top of a cliff that is 111 meters high with a horizontal speed of 33 meters per second. So first thing we want to do is we want to draw a picture of our problem. So I'm going to go ahead and do that down below. I see here's my cliff. Here's my rock being thrown from that cliff. My cliff is 111 meters tall. If I'm going to set an origin, I want that origin to be right at the bottom, pointed up in the positive direction, and to the right in the positive x direction. Next, I'm going to go ahead and label my initial velocity. It says that it's being thrown with a horizontal speed. Horizontal is referring to the x direction, and that speed is 33 meters per second. It's going to land somewhere over here. I'm not entirely sure where, but I do know that when it does land, it's going to land at a height of 0 meters because this height right here is at the height of my origin in the y direction. So let's go ahead and fill out our table above. So the initial distance in the x is just 0 meters because we're starting at the origin in the x direction. The origin's right here. So right here in the x direction is the same, okay? The final distance in the x direction, we don't know that at the moment, so we're just going to leave that blank. The initial velocity in the x direction, well, it tells us that's 33 meters per second. So I'm going to go ahead and put that here. The final velocity in the x direction, well, in order to know that, we need to remember that what the acceleration is in the x direction. The acceleration in the x direction is just 0. The reason being, the only forces acting on this object when it's in the air is going to be gravity. And gravity only points down. So nothing is going to impact the horizontal component here. Therefore, our final velocity in the x direction is the same as our initial velocity in the x direction, 33. Next, we're going to take a look at our y. And for the y values, we said that our initial distance is our height. That height is 111 meters. The final distance, our rock is landing on the ground, so that's 0 meters. Our initial velocity in the y, well, initially it's only being launched horizontally. So our initial velocity in the y should be 0 because it's not falling down in the beginning. It's being shot out horizontally in the x direction. The final velocity in the y is unknown. Acceleration in the y is negative 9.8. And the reason being, this is just gravity. Now that we have only two missing variables from each side, we can start to solve. We can look at the x direction and see if we can solve there first, and then make our way to the y direction. If we look at the x direction, we need to remember that the only equation we can actually use is big dog here. And for big dog, that means that we can only be missing one variable. Well, we're missing df and we're missing t, so we're not going to be able to start this problem in the x direction. If we tried to use little pup in the x direction, we would just get 33 equals 33 plus 0 times t. This just tells me that 0 equals 0, which I know because that's just common sense. So what that means is that we're going to have to use the y direction here. For the y direction, we can start off with looking for an equation that's either missing velocity final or time. So we could either do big dog or shaggy cat. I'm going to do big dog because that's the one that I want to go with. So for big dog, I have my equation here, df equals do plus vo times t plus 1/2 at squared. I plug in my values, df is 0, do is 111, vo is 0, times t, so this is all just 0, plus 1/2. A is negative 9.8, and t is what I'm solving for. I simplify, I subtract 111 over, I get negative 111 is equal to negative 4.9 times t squared. Divide by negative 4.9, and I find out that t squared, or that t is equal to the square root of negative 111 divided by negative 4.9, gives me 22.65. So t equals the square root of 22.65. And that answer is just 4.76 seconds. Now that I know my time, I can go back up here and enter it into my table, 4.76, 4.76. And we know that it's the same time for the x and the y because we're asking for the total launch of that object. And at this time, the object will have the exact same time in the air in the x direction as it would in the y direction. Now we can use that information to solve for our remaining variables. Let's solve for the velocity final in the y direction first. So to do that, we're just going to use a little puff. So we get Vf equals Vo plus A times t. I find out that Vf is equal to 0 plus negative 9.8 times 4.76. That gives me a Vf of negative 46.65 meters per second. Now I'm going to go ahead and take this number, add it up here back to my table, 46.65. The only thing I'm missing now is my distance final in the x direction, so I'm going to go ahead and solve for that now. And my distance final in the x is just going to use big dog. Big dog in the x, when we're in the air, is just df equals, well, we know do is 0, so we can leave that out, vo times t plus 1/2 at squared. We know a is 0, so we can leave that out. This is the only equation you can actually use in the x direction when an object is in the air, because all the other equations just turn to 0. Therefore, if I plug in my numbers here, I find out that df is equal to 33 times 4.76. That gives me a final distance of 157.08 meters. Now that I have all of this filled out, I can go ahead and answer the next part. The next part is asking for my total initial and final velocities. Well, when we're referring to total initial and final velocities, we're just talking about our triangles here. So in the beginning, our total initial velocity is just our x velocity, because we can see that we only have velocity in the x direction in the beginning. Therefore, that would just be 33. Well, if it's only in the x direction, that angle is just 0 degrees. And the reason being, if this is our graph here, the angle that our horizontal velocity makes with that, there isn't an angle. It's just 0. Next, if we look at the final, our object is hitting the ground at this angle, right? It's looking like this when it hits the ground. It's forming an angle right here. How do I know that? Well, I know that because my horizontal velocity looks like this at the end, so Vf of x, and my vertical velocity of y looks like this. It's pointed downward. Therefore, I can see that I just formed a right triangle. So I have my angle here that I'm trying to solve for, as well as my hypotenuse, or my total final velocity. So the first thing I can do is either solve for the angle or solve for the missing side. I'm going to solve for the angle first, and the way I'm going to do that is with inverse trig. So solving for the angle, I end up with inverse tangent is equal to opposite, in this case VFY, over adjacent VFX. All of that is equal to my angle. I plug in my numbers, I get tan inverse of negative 46.65 divided by 33. This gives me an angle that's equal to negative 54.72 degrees. So I'm going to go ahead and put this angle up here. Notice that it's negative, and the reason it's negative is because when our projectile hits the ground, it's hitting it under the horizontal. So this line right here is considered the horizontal. And to express a negative angle, that means that we're just going clockwise from the horizontal. So if I said 54 degrees, well, 54 degrees would just be the opposite of that. That would be pointed in this direction. That's not the case. In this case, we're pointed under the horizontal. Next, we need to find out what our total final velocity is. And for that, we can just use Pythagorean theorem. And Pythagorean theorem is just going to tell us the following: a squared plus b squared equals c squared. In this case, our a squared is our velocity final in the y direction, and our b squared is the velocity final in the x direction. I can plug in my numbers and solve here. The most important thing, though, that people make mistakes on when it comes to this type of problem is remembering when they plug this into their calculator. You need to plug in the velocity first, and I recommend doing it in parentheses and then squaring it, because that's something that a lot of people will mess up on, and their calculator will give them the wrong answer because of it. So make sure that you have that negative sign inside the parentheses so you don't make silly mistakes. You find out that your total final velocity is equal to 57.14. Again, this number is realistic because it's bigger than both of these. It's the hypotenuse here. It's the combination of my x and my y final velocities. Now that we've answered all of the questions in our table, we can just go ahead and look at the questions on the problem. So the first one says, how long will the rock be falling through the air? Well, I figured out that time is going to be 4.76 seconds. Next, how far from the base of the cliff does the rock land? That's talking about the distance in my x direction, and that would be 157.08 meters. The next one says, what is the final vertical velocity of the rock? Remember what direction it's going in. So that's giving us a hint that it's pointed down, and down is negative. I figured out that final velocity in the y direction is negative 46.65 meters per second. Our next question is, what is the final horizontal velocity of the rock? Well, that's a funny question because it's the same as the initial final velocity. Because it's the same as the initial x horizontal velocity of the rock, because it's not accelerating. So this is the same answer. Lastly, what is the total final velocity of the ball? Well, we said that, right? The total final velocity is right here, 57.14. And we found that out again because we had a triangle that looked like this. And our final velocity, our total final velocity, was the hypotenuse of that triangle, where we had our final velocity in the x and our final velocity in the y. Because it's velocity, though, it's a vector, so we needed an angle to say what direction it was pointed in. And we figured out that angle was negative 52.72 degrees.